Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in this lecture, that is Introduction to epsilon-NFA, we are going to start with the third type of finite automata, which is epsilon-NFA, or we can say it as NFA with epsilon transitions. So let's see all the topics of this lecture. Our first topic is Introduction to epsilon-NFA, in which I will explain you the formal definition of epsilon-NFA, and we will also discuss the needs of epsilon-NFA. Our second topic is epsilon closure in epsilon-NFA, in which we will understand what is an epsilon closure and how to calculate it. So let's begin with our very first topic, that is Introduction to epsilon-NFA. So, we already know the basic classification of finite state machines. Finite state machines or finite automata are broadly classified into two categories, acceptors and transducers. Acceptors are further classified into three types, DFA, NFA and epsilon-NFA, out of which we have already completed deterministic finite automata and we have already completed non-deterministic finite automata. And now we are going to proceed with the third type of finite automata without output, that is epsilon-NFA. But we will not directly jump into the formal definition of epsilon-NFA. Before that, I will develop a basic intuition regarding epsilon-NFA. So you all know what is a deterministic finite automata. I have told you, in case of DFA, for every current state, there is only one next state for a given input symbol. Also, every state should have a transition for every input symbol, and in DFA, there is no epsilon transitions. So every transition is caused by an input symbol. And in case of NFA, for every current state, there can be more than one next states possible. Like here you can see for the state Q2, we have one next state as Q0 and one next state as Q1. So there are two next states for the same input symbol A. That means in case of NFA, we can have more than one next states for the current state on the same input symbol. Also, in case of NFA, it is not necessary that every state should have a transition for every input symbol. Like the state Q1 doesn't have a transition for input symbols A and B, so it is allowed in NFA. And like DFA, in case of NFA also, epsilon transitions are not allowed. That means every transition should be caused by an input symbol. Now let's proceed with the major agenda of this lecture, that is epsilon-NFA. As the name suggests, epsilon-NFA, which means it is a type of NFA. So it will inherit all the properties of NFA. Like NFA, in case of epsilon-NFA also, for every current state, there can be more than one next states possible. Also, it is not necessary that every state should have a transition for every input symbol. But there is a slight difference between NFA and epsilon-NFA. In case of NFA, I told you that every transition should be caused by an input symbol. That means there cannot be any epsilon transition or null move in case of a regular NFA. But in case of epsilon-NFA, epsilon transitions are allowed. That means you can move from one state to another state without even reading any input symbol. So such transitions are called as epsilon transitions, and that is allowed in epsilon-NFA. Now let's understand more about this epsilon. Epsilon is not a part of input alphabet sigma. So reading the symbol epsilon means reading no input symbol. We already know what is sigma, that is our input alphabet. It is simply the set of input symbols. And we know the input symbols can be 0, 1, 2, A, B, C. But epsilon is not a part of input alphabet. Epsilon is not any input symbol. That is why reading the symbol epsilon means reading no input symbol. So if I say that I can move from the state Q0 to Q1 by reading epsilon, it means that I can move from the state Q0 to Q1 by not reading any input symbol. Let's see the next point. Epsilon-NFA is an extension of NFA, introducing epsilon transitions, where the machine can also change states without reading any input symbol. What does that mean? It simply means that epsilon-NFA is an extension of NFA. I already told you, epsilon-NFA is a special type of NFA. So it will have all the properties of NFA, but there is a slight difference. In epsilon-NFA, epsilon transitions are also allowed. Means the machine can also change states without reading any input symbol. Like we have seen in this diagram, machine is able to make the change of states without reading any input symbol because epsilon is not any input symbol. So I hope a basic intuition regarding epsilon-NFA is clear to you. Now, such transitions involving the symbol epsilon is called as epsilon transition or null move. Now we are all set to understand the formal definition of epsilon-NFA. An epsilon-NFA is a non-deterministic finite automata in which transitions can occur either on input symbols or without consuming any input symbol. The transitions without input are called epsilon transitions or epsilon moves or null moves. Now, if you are clear with the basic intuition of epsilon-NFA that I have just given you, understanding this formal definition is a very simple task for you. Let's see. An epsilon-NFA is a non-deterministic finite automata. This I have already told you, that epsilon-NFA is just a type of NFA in which transitions can occur either on input symbols or without consuming any input symbol. So obviously, machine can change the state from one state to another state by reading any input symbol, like NFA. And machine can even change its state from one state to another state without reading any input symbol. And that's the beauty of epsilon-NFA. The transitions without input are called as epsilon transitions or epsilon moves or null moves, which simply means that such transitions without involving any input symbol are called as epsilon transitions or null moves, or we can also call it as epsilon moves. I hope the formal definition of epsilon-NFA is clear to you. Now we are going to understand the 5-tuple representation of an epsilon-NFA. Let's see. The 5-tuple representation of an epsilon-NFA is given by n, which is our epsilon-NFA, is equal to q, sigma, delta, q0, f. These 5 elements are used to entirely represent an epsilon-NFA. And if you observe carefully, this 5-tuple representation of epsilon-NFA is identical to the 5-tuple representation of DFA as well as NFA. Then what's the difference? The difference is only in the transition function delta. Let's see. The transition function of epsilon-NFA is given by delta q cross sigma union epsilon gives us 2 to the power q. Now in case of NFA, in the transition function of NFA, here we were only having sigma, that is our input alphabet. But in case of epsilon-NFA, we have taken the union of sigma with epsilon because in epsilon-NFA, the transition can occur due to an input symbol and transition can also occur without consuming any input symbol. That is an epsilon transition. And to denote this, we have taken the union of sigma with epsilon. So this is the transition function of epsilon-NFA. I hope the 5-tuple representation of epsilon-NFA is now clear to you. So let's see the last point. every state on getting epsilon goes to itself. What does that mean? It simply means that for every state, it is implicit and by default that if this state gets the epsilon, it goes back to the same state. So it is implicit and we do not need to draw a self loop over the state Q0 to show the epsilon transition towards itself. So you have to remember that every state on getting epsilon goes to itself. I hope the formal definition of epsilon-NFA, the 5-tuple representation, the transition function, and this point is now clear to you. Now we will discuss the need of epsilon-NFA. Obviously, if you are understanding a topic, it is very important to know what is the need of understanding that topic. So let's see, why do we need epsilon-NFA? Epsilon-NFA provides more flexibility in automata design, as it simplifies the construction of complex automata. What does that mean? If we want to draw a complex automata, it is very difficult to draw that complex automata in one go. That is why we divide that complex automata into smaller parts, and we can design each of the smaller parts separately. Now, after designing each smaller part separately, to get the resulting complex automata, we need to combine those smaller parts together. And to combine those smaller parts together, we use epsilon transitions. That is why epsilon-NFA provides flexibility in automata design to simplify the construction of complex automata. Let's see the next point. Multiple automata can be combined easily using epsilon transitions. I have already told you that if we have multiple automata, we can combine them together to convert a fully fledged automata using epsilon transitions. Let's see the next point. Epsilon-NFA is commonly used while converting regular expressions into finite automata. Now, when we will understand the chapter number 3, that is regular expression, there is one important topic in that chapter, that is to convert the regular expression into its equivalent finite automata. So, sometimes the regular expressions are very big. So, it is not possible to convert the big regular expression into one finite automata in one single go. That is why we divide that big regular expression into multiple parts, and for each sub-part of the regular expression, we draw a finite automata. And after drawing all the separate finite automata, we combine them together to get the resulting finite automata for the given regular expression. And that is why epsilon-NFA, or we can say epsilon transitions, are used to convert the regular expressions into its equivalent finite automata. This is how we have understood the need of epsilon-NFA. In this way, we have completed our first topic, that is Introduction to epsilon-NFA. Now we are going to proceed with our second topic, that is epsilon closure in epsilon-NFA. But what is the need to study epsilon closure? From the next lecture onwards, we will start a very important topic, that is the conversion of epsilon-NFA into its equivalent NFA. And in that conversion, in each step, you will calculate the epsilon closure of epsilon-NFA states. That is why in advance, we are going to study epsilon closure and how to calculate epsilon closure for the different states of epsilon-NFA. So let's start it. Epsilon closure of a state Q, denoted by epsilon closure Q, is the set of all states reachable from the state Q using only epsilon transitions, including the state Q itself. You may find this definition a little bit complex, but don't worry, I will decode it for you. Let's understand. Epsilon closure of a state Q, which means that epsilon closure is only calculated for a particular state of epsilon-NFA. And it is denoted by epsilon closure within the brackets the name of the state, that is Q here. It is the set of all states reachable from the state Q using only epsilon transition. That means epsilon closure is basically a set. Set of what? Set of only those states that we can reach from the state Q using only epsilon transitions. This definition will become more clear to you once we see an example. So this is an example of epsilon-NFA, and you can see these two are the epsilon transitions. Now if I tell you to calculate the epsilon closure of the state A, how do we calculate? According to the definition, the epsilon closure of the state A is the set of all states that we can reach from the state A using only epsilon transitions. So, what are the states that we can reach from the state A using only epsilon transitions? We can see that we can reach the state B from the state A using only epsilon transitions. That is why B will be the part of epsilon closure of A. Similarly, we can reach from A to the state D using only epsilon transitions. That is why D will also be the part of epsilon closure of A. Can we reach the state C from the state A using only epsilon transitions? Many of you may think that we can take this path to reach the state C, but this is an epsilon transition, that is fine. But this is not an epsilon transition. This transition is involving an input symbol which is 0. That means C will not be the part of epsilon closure of A. And now let's come back to the definition. It is written including the state Q itself. That means the epsilon closure of the state A will also contain the state A itself. So finally, epsilon closure of A is the set of states A, B and D. A itself will be the part of epsilon closure as per the definition, and the states B and D are the states that we can reach from the state A using only epsilon transitions. Now let's calculate the epsilon closure of the state B. So what are the states that we can reach from B using only epsilon transitions? Can we reach the state A from the state B using epsilon transitions? No. This transition is an incoming transition. This is not an outgoing transition. So A will not be the part of epsilon closure of B. Will C be the part of epsilon closure of B? No. There is no epsilon transition from B to C. That is why C is not the part of epsilon closure of B. But we can see from the state B, we can reach the state D using only epsilon transition. That is why D will be the part of epsilon closure of B. And according to definition, B itself will be the part of epsilon closure of B. So finally we will get epsilon closure of B equal to B comma D. Now let's calculate the epsilon closure of the state C. You can clearly see we cannot reach any state from the state C using epsilon transition. That is why the epsilon closure of C will only contain itself. And similarly, the epsilon closure of D also will only contain the state D itself, because we cannot reach any other state from the state D using epsilon transitions. Here you need to note that these are not the outgoing transitions. These are the incoming epsilon transitions. So don't get confused with that. We are not having any transition from the state D to reach any other state. That is why epsilon closure of D only contains the state D. This is how we calculate the epsilon closure of a given state in an epsilon-NFA. I hope you have understood it. In this way, we have completed our topic epsilon closure in epsilon-NFA. But before I end this lecture, I have one homework problem for you. Find the epsilon closure of all the states of the given epsilon-NFA. So this is a new transition diagram of an epsilon-NFA that I have taken for your homework, and you need to calculate the epsilon closure of all the states of this epsilon-NFA. And after solving this problem, you need to post the answers for the epsilon closure of all the states in the comment section. In this way, we are done with our topic, epsilon closure in epsilon-NFA. From the next lecture onwards, we are going to understand the conversion of epsilon-NFA into its equivalent NFA. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.